Okay, yeah, so thanks a lot for inviting me to give this talk. You know, it's been 2 years since I was at an in-person conference, so this is just great. First of all, you know, what is T2K? T2K is, first and foremost, a group of people. We have 500 members from 76 institutions and 13 countries, including CERN, or not including, plus CERN. And this was the last time that a large fraction of us were all together, so it's July 2019 on a ridiculously hot day in Paris. And T2K is also an experiment. So it has 3 major components. So we produce an accelerated neutrino beam on the east coast of Japan in the J-Park facility. We sample the unoscillated beam at a near detector, and then we sample it again 295 kilometers away in the Superchemia Kanda detector. So in this talk, I'll give a little bit more information about all these sort of major players. I'll talk about the oscillation results, the most recent oscillation results. I'll say a little bit about recent cross-section measurements, and I'll touch on future plans when I conclude. Okay, so the first component to talk about, which is common essentially to all accelerated neutrino experiments, is the neutrino beam. So we produce them in similar ways. We have an initial proton beam that collides onto, in our case, a graphite target, and that produces a spray of secondary particles which are focused by a series of electromagnetic horns. And though the secondaries are allowed to decay, and that produces our neutrino beam. Now we monitor the neutrino beam in a number of different ways. So we monitor the proton beam. We have obviously done surveys of the horn and beam alignment. We monitor the horn current and field. We monitor the beam direction with one of the near detectors, which is dedicated for that purpose, which I'll say a little bit more about on the next slide. And what's new and exciting for this 2020 analysis, which is what I'm presenting here, the last public results, is we dramatically updated our constraints on the hadron production. So the NA61 and SHINE experiments at CERN use a replica version of the T2K target and impinge protons upon it, and then measure the hadrons that are coming out. And so by taking those measurements, we were able to reduce the uncertainty on our incoming neutrino flux from the dashed black line here to the solid black line, right? And this is as a function of the true neutrino energy, and you see the rate overlaid as the gray histogram, so you can see where our flux peak is. This is a change from about 10% uncertainties to about 5% uncertainties. The other interesting feature to note about the T2K beam is that we're off-axis. So the neutrino, the beam direction is not pointing straight at Super K. It's 2.5 degrees away from Super K, which is about 12 kilometers, I think, at the Super K distance. And the reason we do this is because as you go off axis, because of kinematics of pion decay with a maximum transverse component, you reduce the flux peak, but you also tighten it up. So we have a very nicely focused flux peak here, shown in red. Okay, so the second of these sort of major components of the experiment, the near detector complex, I showed briefly the Ingrid detector on the previous slide. So this is a detector which is in the shape of a cross and centered with the sort of intersection of the cross at the beam center, and this allows us to monitor the beam direction very accurately. Most of what I'll talk about in this, most of what I'll talk about later in the talk refers to the ND280, the off-axis near detector. This is a series of different detectors, 2.5 degrees off-axis, so the same off-axis angle as Super K is. Mostly what I'll talk about are these guys here, which are labeled FGD, so it's a fully active tracking scintillator detector. We call it the fine-grained detector, although it's only fineness is relative. And then FGD2, which has passive water layers as well. I won't say too much about it, but what's new for T2K, or fairly new, is the Wagashi detector, which is 1.5 degrees off axis. And this is really going to allow us in future to start tightening up our understanding of how cross-sections and interaction physics changes as a function of neutrino energy, right? Because by having a different off-axis angle, 1.5 degrees, we have a different flux, but with all the correlations. And the final player, if you like, is Super Kamiokande, which I'm sure we're all familiar with, but it's always nice to see these beautiful pictures. So it's a 50,000 tons of ultra-pure water, 27.2 kilotons of which are fiducial for T2K analyses. It's very low background, deep underground. It has an excellent 40% photocathode coverage. And essentially what we use Super K for is for differentiating between muon-like and electron-like Cherenkov rings. And so what's shown in the top right figure here is Super K's PID for discriminating between these two. Essentially, it's telling the difference between the very sharp muon-like ring and the more fuzzy electron-like ring caused as electrons rescatter at the detector. But you can see there's the really excellent separation between the green and the orange populations. So I'll make a note now, a slight detour, but I'll come back to it later, so hopefully you'll see why, and how Super K does energy reconstruction, right? So it's a Cherenkov detector, so it has a fairly high tracking threshold for some particles. So all we see in an interaction typically is the outgoing lepton. And so we try and reconstruct the neutrino energy through this formula, which essentially is assuming two-body kinematics. And with a known neutrino direction, you can get back to the neutrino energy. But it makes the assumption that the neutrino is scattering off a nucleon that is at rest. And also that there's no other particles produced in the initial interaction. So if we look at this plot here, it shows the T2K flux versus the neutrino cross-section split into different components. So the CCQE is essentially this diagram here. But we also are in a region where we have CC resonant production. So we produce an excited state of the nucleon, which decays to produce pions and protons or neutrons. And we also have some DIS contribution in the tail. So is this a reasonable approximation? Well, it works fairly well, but we have to include all sorts of effects. So it's not a free nucleon, it's not at rest. We have to include nuclear state effects, the nucleons are in motion. There are additional nuclear effects that are sort of, you can have quasi-bound nucleon-nucleon states inside the nucleus. And also, perhaps most importantly, final state interactions confuse what we observe in the detector with what was actually produced at the vertex. So even though you might have one of these guys, a resonant interaction, you produce a pion, you might not see it in the detector because it might be reabsorbed inside the nucleus before you have a chance to see what's going on. So what we measure is not this CCQE, but we measure CC0 pi. And I'm going to return to this several times throughout this talk. Okay. And so the T2K has been running for about a decade now, or over a decade. What I'm showing in this plot is the accumulated POT over time and the beam power. And the results I'm going to show use results up to 2020, up to here, which is 3.6 times 10 to the 21 POT in total, split more or less equally between neutrino and antineutrino. And what's different with respect to our previous result, which was this Nature publication and corresponding PRD, is 33% more neutrino mode POT, and also revamped systematics. Okay. So let's kind of introduce the sort of players that I'm going to keep referring to throughout the talk. So I'll go into a bit more detail about the oscillation analysis. So what are we trying to measure with T2K? What essentially are we looking for? Well, there are two different oscillation channels we look at. So first of all, we start off with a predominantly muon neutrino or muon antineutrino beam, depending on the polarity of the focusing horns. And I've written the leading order oscillation probability here for still finding muon neutrinos at some distance away from the production point. And you see it can be written as an amplitude and a phase. And this phase depends in this phase term, there's the distance and the neutrino energy, but we have a fixed baseline, so it looks like an energy-dependent effect for us. And so what's shown here, actually for a slightly earlier data set, but it's a nicer plot to use for this example, is the difference between the unoscillated prediction for the nu mu spectrum, and the oscillated spectrum and our data, right? And this is the ratio. And that really shows you this characteristic oscillation dip. And so what we do is we measure the depth and the position of this dip, and that gives us the amplitude in the phase. The other channel we look at, electron neutrino or antineutrino appearance. It's a more complicated equation, and I've truncated it, so don't fixate too much on it. But what I want to highlight is we start to get sensitivity to the CP violating phase. So we have a sign change here for neutrinos and antineutrinos. And what this plot shows is the oscillation probability overlaid with our initially muon neutrino flux prediction. And so what we're looking for basically is the difference between the different delta CP scenarios shown there. Okay, so how do we do this? So on this slide, I've basically shown two different and complementary ways for how we can describe an oscillation analysis. So I'll start with this one in the lower left. So what do we measure in our detectors? You know, I've described the near detector and the far detector, but what are we actually measuring? So at the near detector, right, in both we measure a rate, right, as a function of observables in the detector. And at the near detector, that rate is a convolution of the flux, the cross-section, and the detector efficiency and smearing, all convolved and integrated over the incoming neutrino flux. And at the far detector, that is also convolved with the oscillation probability. So clearly, the near detector is going to give us some relevant information about the flux, the cross-section, and potentially the detector as well. But these aren't going to trivially cancel because of this integral, right? And the flux spectrum is changing. You know, that's the whole point of the experiment. So another way of looking at this, which I'm going to sort of come back to repeatedly during this talk, is you know, we have a model for all these pieces. We have a cross-section model, a flux model, detector model, and then we have data. And so what we do in the analysis is we take these models, we convolve them, we constrain them at the near detector using near detector data in a near detector fit. Then we take that to the far detector, include you know, far detector data and the detector model, and in the oscillation fit there, extract oscillation parameters. One thing I'm not going to talk about any further is the importance of external cross-section data. So we inform the cross-section model just as we inform the flux model. You know, I described the Na61 shine data constraining the flux model using with a hadron production experiment. We also do this for the cross-section model using all the other data we can get our hands on. So all the other talks about, you know, currently operating experiments, we take the output for, you know, the cross-section outputs from those experiments to inform our model. We can't use our own, of course, because then we'd add some sort of weird circularity. Okay, so I'm going to talk about these one at a time. So I'll focus first on the near detector data and how that constrains these parameters. Okay, so firstly at the near detector, we have a very high rate because we're so close to the production point. So we're able to subdivide the data in a number of ways, and we do that based on the number of final state piles. So what's shown here is a zoom in of the inner tracker of that off-axis ND280 detector. So this is that fully active tracking scintillator detector, FGD1, and this is the FGD2, which includes passive water targets. And so we subdivide and say, okay, this is a CC0 pi event. This is a CC1 pi event. We see a muon and a pi plus. And this is CC other, which is kind of a catch-all for more complicated events with more than one pi. So we have these samples for neutrino and antineutrino enhanced modes. And we're also able to split into mu plus and mu minus. So essentially whether you have whether it's neutrino or antineutrino, you know, right or wrong sign contamination in the beam, because it's a magnetized near detector. And we include samples on the plastic here and the water plastic mixed targets to constrain the rate on water, which is of course of utmost importance because we have water at the far detector. And so if we take our a priori model for detector cross-section and flux parameters and look at our prediction for one of these samples here, which is the muon neutrino CC0 pi on plastic, as a function of the muon momentum, we will get the shaded histogram. Then we look at our data, and that's the data points on this left-hand plot. And so, it doesn't agree perfectly. You can see the ratio at the bottom here. And then we do a fit, and it's simultaneous to all of these samples. It's actually as a function of the muon momentum and the muon angle with respect to the incoming neutrino beam. And by construction, we get a better agreement. But what we've done is we've updated our a priori prediction of the flux, the cross-section, and the detector systematic parameters with our data, right? And one thing I kind of glossed over, but maybe I should have said, is that by separating our sample up in this way, we kind of we managed to break those degeneracies that maybe were obvious from the equations I showed before. Flux and cross-section can sort of account for each other, but when we split up the sample, these have different contributions from different cross-section parameters, but the flux affects them all. So the impact of the near detector fit, when we look at this sort of horrible covariance, don't look too much at it, which is the flux and the cross-section parameters before the fit. We see, so the flux is strongly correlated between, these are in energy, flavor, and detector bins, so the sort of near detector and far detector included in this very correlated matrix. But initially, there's no correlation with the cross-section. By doing this fit, one of the major impacts is that we introduce anti-correlation between the cross-section and the flux, right? So all the blue on the right-hand plot. And then we want to propagate that to super K. So the super K flux prediction is correlated with the near detector flux prediction through the B model. So when we update our understanding of the near detector flux, we can update our understanding of the far detector flux. And that's what's shown here, just for the muon neutrino flux in neutrino enhanced mode at super K. And you see that the fitted flux parameters mostly agree within 1 sigma, although obviously there are correlations here, so it's hard to really judge from this plot. After the near detector constraint compared to before the near detector constraint. So that's reassuring, but it has been updated. And if we look at the predicted rate distribution, I've somehow clipped the axis, sorry about that, as a function of the reconstructed neutrino energy, we see that we've pulled around our prediction, but we've also really tightened up our uncertainties. And actually now the uncertainty on the flux and cross-section is less than the super K detector uncertainty, which is very important for the power of our oscillation results. Okay, so I'll talk a little bit about super K data now. So I showed a plot similar to this a couple of times. We have 5 samples that we use in the fit at super K. We have neutrino enhanced mode, single muon-like ring. It's not a magnetized detector, so we don't know if it's mu plus or mu minus. And we have the same in anti-neutrino mode. So what's shown here is actually this is the fitted spectra with the uncertainty against the data and the ratio with respect to the unoscillated prediction. So you see the characteristic oscillation dip I was highlighting before. And so, okay, we look for a single muon-like ring and we allow one decay electron, which is just whether the muon stops inside the detector or not. And I've already introduced the reconstructed neutrino energy. We also have 3 electron-like samples in the fit. So the neutrino mode single electron-like sample, we look for 1 electron-like ring. Same in anti-neutrino mode. We don't allow a decay electron in these cases because there's no Michel. However, since 2018, we've included a 5th sample in the fit where we do include a decay electron. And this is for the case where there's a pion produced, which is below Cherenkov threshold, but we see its decay. And of course, in this case, the reconstructed neutrino energy equation changes to accommodate the intermediate delta. Okay. Oh, actually, one thing I should have said is that, well, it's a detail, but in the fit, we've been not just in reconstructed neutrino energy, but also the angle with respect to the incoming beam. Okay, so now the oscillation fit and results. So, I showed this equation before, and I showed this as a cartoon. Now this is just the same, but with the real results. So again, we look at the amplitude and the phase of this equation. Although I should note we don't fit the disappearance samples, the muon neutrino samples separately. We fit all the samples together and extract all the oscillation results at the same time. So what's shown on the right here is a 90% confidence interval. Well, actually, no, several confidence intervals in fitting in normal and inverted ordering separately, again as a function of the amplitude and the phase. One thing I'll note is that this is sine squared theta 2,3 rather than sine squared 2 theta 2,3, which is by convention because this appears in the leading order appearance probability. But this is something as a function of theta 2,3. I guess you can see it's not too important. And delta m squared 3, 2. The other projection that we generally show in the appearance parameters is a function of delta CP and sine square theta 1,3. And we run fits in two scenarios, with and without including a prior constraint on the value of sine square theta 1,3, which comes from the PDG, which is just from reactor experiments and mostly diode-based. And so when we run the fit without a constraint in the top here, and again, these are confidence intervals for various degrees of confidence, we get a consistent value with the PDG value of sine squared theta 1,3. And I'll also draw attention to the fact that without the constraint, we still have closed 90% confidence limits on delta CP, or in this plane, let's say. If we apply the reactor constraint, so we include it as a constraint in the fit, and note the scale change between these two plots, the gray band has the same width on the two different scales. We obviously tighten up the distribution a lot because we're adding more information. But we haven't radically changed our best fit points. We still have a preference for delta CP of about -pi/2. Now, if we just look as a function of delta CP, shown here, so delta CP versus the delta chi-square, shown for both normal and inverted orderings. So we fit separately. The curves are shown relative to the global minimum, but the confidence limits are separated by a hierarchy. And you see that delta CP, conserving values, 0 plus minus pi, are excluded at about 2 sigma. Not quite. There's a little bit still allowed there. And we have a mild preference for normal ordering. I've included these plots just in case you want to see where this preference for -pi/2 comes from. So -pi/2 is the red in these two plots. CP conserving is the gray, and plus pi/2 is the blue. So you see that in the neutrino mode, we clearly have a preference for higher for the CP conserving values, which is more consistent with -pi/2. So we can compare these results with other experiments. So T2K, the results I've shown here are in blue. I've included NOVA and Super-K results from 2020 and a slightly earlier IceCube result. You see T2K has world-leading results in the delta m square 3,2 sine square theta 2,3 plane. It also has a world-leading delta CP constraint. Interestingly, if we look at these plots as a function of delta CP versus sine square theta 2,3, we have a slightly different 90% confidence interval to NOVA, so the blue versus the red. But it's really too soon to talk about tension. There's still quite a lot of overlap. And these are only 90% confidence limits. So I'll only briefly touch on this, and I think we'll hear more in the next talk. There are benefits from combining T2K with these other data sets. We talk about how we compare, but really they're complementary. We have different systematics, maybe different beam energies. and maybe different sensitivities to some of these parameters. And so we're currently working on combining T2K with other data. So I think in Zoya's talk, we'll hear about efforts to combine T2K and NOVA. And I just wanted to highlight that there's an ongoing T2K plus Super K atmospheric analysis ongoing, and this plot just shows the relative sensitivity of T2K and Super K as a function of delta CP. So clearly by combining the two, we'll get more information overall. So that concludes my section on oscillation results. I don't know, we can have questions now, or maybe I should just go through. Okay, I'll just continue. Okay, so if we talk about neutrino cross-sections, what can we measure? So I showed this equation before. And at the near detector, we measure the rate, and it's a convolution of the flux cross-section and this detector efficiency. And this rate comes from a few different cross-sections, right? We have CCQE, we have resonant interactions, we have deep and elastic scattering. But what we can measure in the detector is as a function of, what is what we can see, right? So we can say there's no pions in the final state, or one pion in the final state, or break down by the number of protons. So we don't actually measure this quantity. We can't. We rearrange this equation, and what we get is a cross-section as a function of detector observables in some interaction topology. And this is a summation over these different sort of fundamental interaction channels, these guys, convolved with some final state interaction probability, and excuse the very poor notation here. And all of this is integrated over the broad neutrino flux. So it's quite a complicated object. Our general strategy is to build selections of these interaction topologies by adding restrictions on outgoing hadrons. So doing the same thing that we do in the oscillation analysis. The advantage of this is there's no model-dependent corrections. We're not trying to take CC0 pi and remove everything that's not CCQE, which would add our own model. But by splitting in this way, we can kind of subdivide our sample based roughly on increasing energy transfer, which corresponds approximately with the number of pions in the final state. So initially, we measure electron kinematics, and we're adding hadron kinematics over time. And what we're trying to do, and I'll highlight this in the next couple of slides, is benefit from the fact we have different fluxes available to us and different targets at the near detector. And our overriding principle is to avoid model dependence. And if you want to know more about that, I'm always happy to rant over coffee. So I'll just highlight a couple of our recent results very quickly to give you a flavor of what we're doing. So one of our recent results is CC0 pi, looking at muon neutrinos and muon antineutrinos in a correlated way. So we use the same selections that we had using the oscillation analysis for CC0 pi. And that's shown here for, on the plastic in FGD1. So this is shown for the neutrino sample and the antineutrino sample here. It's not entirely pure. We have some background contamination. So we include samples in the analysis to constrain some of the major backgrounds. So CC1 pi, where we don't see the pion, but it does go outside the nucleus, and CC other as well. And so this is correcting for misreconstruction effects. Now, when we extract cross sections, we produce cross sections as a function of a large number of kinematic bins. So this is in slices of cosine theta mu as a function of the muon momentum. And by including both neutrino and antineutrino samples, we can fairly strongly differentiate between different model predictions. In fact, I'm not sure how well you can see those chi-squares, but the chi-squares are not great considering we have a total of 116 bins extracted. Although this is just the neutrino mode version shown here, but the chi-square includes all of them. I'm going to skip the next slide. This just shows that we can, by combining the neutrino and antineutrino results and by exploiting the correlations, we can get additional sensitivities to these different models. I think I'll skip that in the interest of time. And we also have a similar analysis where what we do instead of neutrino and antineutrino, we have neutrino on plastic and neutrino on water. And by extracting the cross-section using those two samples simultaneously, we can have a correlated result of the cross-section on carbon and oxygen, which allows us to get at the atomic number dependence of the cross-section. So this is just to give a flavor of what we're trying to do and why we're trying to do it. You know, we're interested in how cross-sections scale with atomic number because we have lots of different experiments running on with different targets. So the next steps in this approach are to combine these sort of two methods, neutrino, antineutrino, hydrocarbon, water, and then to start looking at the multiple detectors at different off-axis positions to get at the neutrino energy scaling. I'll skip the next slide and then just say a couple of words. We'll have 1 minute before I finish on T2K's future. So there have been a number of upgrades which are complete or ongoing to sort of ensure we have an exciting program over the next few years. So we have a series of upgrades to the beam, replacing horns, upgrading the power supplies, improving the beam target cooling to allow higher beam powers. So we can go from the 500 kilowatt beam power today to 800 kilowatts in 2024 and 1.2 megawatts in 2027, which is also paving the way for Hyper-K. Super-K has gadolinium loading, which gives us additional sensitivity to neutrons which are captured and produce a delayed signal in the detector, which will allow us to separate right and wrong sign backgrounds in particular. And we're upgrading the near detector, the off-axis near detector, to include higher granularity detectors, and also to get at to improve our detector efficiency in some regions of phase space where previously we were lacking. Probably shouldn't have said lacking. Okay, and I'll just leave the summary slides here and conclude. So thanks for your attention.
All right, thanks for this really nice talk. We have plenty of time for questions or comments. And if you do have a question, raise your hand and I have to run and give you the mic, apparently, for the benefit of the Zoom people. You're closer.
No rush. Okay. Okay, so thank you very much. It was very nice. For this part, when you mentioned about the fit of the near detector data, can you, maybe since we have time, tell us a little bit more and maybe tell us where this fit is ending? I like a lot what you said, namely that you're using the neutrinos and antineutrinos data simultaneously because this reduces a little bit your dependence from the fit. But you said it's a fit which includes cross sections and flux at the same time. Can you give us a feeling of where the fitting is ending? And maybe do you have an idea of how much the fit is affecting your then final results?
So I guess is your concern essentially how this could go wrong or what exactly we're doing in the fit? Okay. So there are limits of the samples we include in the fit. There are some systematics that we don't directly constrain because we don't have dedicated samples for. So one limitation like nu E, nu mu cross-section ratios, we don't have nu E samples in the fit currently. But we try and separate, so for example, one thing that's particularly problematic is what the wrong sign contamination in antineutrino mode is, how many mu minus we have in there. And so adding new samples to the fit gives us additional sensitivity to that. So this sort of strategy of adding new samples and subdividing them in certain ways is kind of focused on giving sensitivity to things that we worry about. So that's sort of the strategy there. I don't know if you wanted to hear more than just an example of that. in terms of the limitations of the fit, maybe sort of the, I don't want to put words into your mouth, but maybe an underlying concern might be, what if we don't have the right flexibility? You know, could we just have a bad fit? You know, one thing that's certainly true is if you try and fit a model to data and you don't have this flexibility in the model, you might, you know, it might look okay, but you might over-constrain certain parameters because you don't have the right flexibility in the model. So we run a large number of post-fit checks to see if we're constraining parameters stronger than we expected based on, you know, sort of doing Asimov fits, fitting the model to itself just to see what we would get if the model is correct. And checking that we're not, you know, massively over-constraining some parameters, checking there isn't tension, which is of course not shown here, right? Just having a fit doesn't mean that it's a good fit. So we do a lot of checks on the post-fit chi-square. And I think maybe another thing that I haven't spoken about because, you know, there's not really time, but we have a lot of extensive, we call them fake data tests. So, you know, we've included a certain, you know, number of systematic parameters. There are maybe others that we can think of, but we can't put them in a fitter because, you know, they're not continuous parameters. You know, it's like a discrete model choice or something. And so what we do is we say, okay, let's reweight, let's transform our model to this alternative, and then fit with the original model and see if we introduce any problems. So by ignoring certain effects that we haven't included, do we get something very strange? You know, do we produce a problem? And we test it all with just sort of Monte Carlo before fitting on data. Other things we do is we take, so we also run tests like if we see a discrepancy in this channel, so we say, okay, this is a surprising difference. It's not, but let's say there's a sample where there is a surprising difference. We could say, okay, we're not entirely sure why this has happened. So let's assume that this is because we have a modeling problem. So let's try and put that in as a fake data study and see what that does to the analysis. So we by construction say, okay, we just add in a generic effect that shores up this problem. And we just push that through the analysis. What would that do to the oscillation contours? You know, so we say, instead of constraining our parameters, we don't really allow it to constrain the parameters. We just put in something that shores up that discrepancy ad hoc based on our own data. And we check that we don't get biased results coming out when we do those sorts of tricks. So I guess, yeah, I guess that's a very long and slightly rambling answer. But we try and check the robustness of the analysis, both in sort of statistical ways, you know, post-fit checks, how well does it work, and also by trying to break it, by adding in changes that we haven't included in the model and seeing if that causes us to produce biased results. Did that answer your question?
Yeah, it was very good that you do a lot of checks and stuff. But if I look at the plot on the right, on the left and the plot on the right, what it seems to me the major effect, and it seems that what is called their quasi-elastic component seems to be much higher. So the final result. So my question was, maybe I was not expressing well, what's the major effect that you needed to change, or parameter or whatever, in the model in order to reproduce the data? By eye, I don't know, I may be wrong, but it seems to me that the quasi-elastic component is changing by a large amount from one to the other. Is that the answer? While the other component seems to be, you know, slightly different, but not much. It would be nice maybe to summarize the result in terms of what is the major change that you need to apply, was something like this.
Yeah, so, okay, there are some, it's difficult when you only look at the plots like this, I appreciate that. So when you change the flux, that will increase all of these. So it's hard to tell whether, just by looking at these plots, whether the effect is by increasing the flux or specifically increasing CCQE. So by subdividing the data, that allows us to attribute the enhancements in the right places. What I would say is in the papers, so there are publications coming out soon for this analysis, and in previous publications, we show how all of the parameters shift around. So I gave one example here of how the Super-K flux shifts around, although this is obviously not directly fitted, but basically the near detector flux in this mode is shifting in the same way. And so you can see actually that we're increasing the flux, which will have an overall effect of increasing all of these guys. We do suppress CC-res, for example, and we do pull around CCQE parameters, but I could show you in a coffee break exactly what's done with the parameters. It is included in the publications, but yeah, I don't have all the details you'd like to see here.
I think Mateus had a question.
So thanks for the nice talk. You had this nice external constraint on the flux, but I'm wondering if you have any plans to use well-known cross-sections to constrain the flux and cross-check that your external measurement matches what you're observing. So I'm thinking of things like neutrino electron scattering or coherent pion production, where you get the shape measurement.
Yeah, so neutrino electron scattering, we don't have a sufficient event rate on T2K. Certainly for other experiments with a larger overall rate, that is being used. But the cross-section is what, like three orders of magnitude lower than the neutrino nucleus cross-section. And we have, order tens of thousands of events at the near detector, maybe 100,000 events. Right, so we don't have a pure enough sample to do that. Sorry, high enough statistics sample to do that, I mean. As far as coherent, so I certainly haven't heard coherent interactions being used on T2K to constrain the flux. I have heard of them being used or mooted to be used in other contexts. And my impression was always that it was unclear whether the cross-section was really known well enough to add information. So one other thing that does get discussed a lot, like the low nu method, is used a lot to go to some region of kinematic space where the cross-section is relatively well known. Although, is it really well known enough to improve upon, I'm going the wrong way. This is, we've set a really quite stringent bar for to improve upon, and so yeah. Essentially, the neutrino electron scattering, not high enough statistics. Everything else, I'm not 100% sure. I personally believe that we can really trust them to the sort of 5% level. But if you disagree, I would love to hear about it.
Yeah, I agree. The low nu method is terrible at these energies. Probably much worse than nu me, for example, because your beam is a much lower energy. Mm-hmm. But so coherent pion production, I think I haven't seen that being used recently, but the idea is that you get the momentum of the neutrino, so you can use that for a shape measurement. So maybe your normalization, you don't know that very well, but you can get the shape. And the reason why I asked this is because so microboon, for example, uses your cross-section too, as far as I understand. So it would be nice to have the flux cross-checked in addition to the NA61 data. But I'm not sure you can do that. That's why I was asking. So I have another question.
Yeah, just 1 second though. Maybe I misheard you, but you said microboon users are tuned. That's not true. They tune their own model to our data.
Oh,
but they don't take the tune. They don't take the fit from our near detector. If that's clear. Okay.
Yeah. Good to know. So the other thing was, I remember in 2020. Oh no, sorry, I'm confused. Never mind.
Okay.
I was going to ask another question.
I think we can take one more last question. So Ivan had his hand up.
Thanks for the nice talk. You were showing the result about delta CP with and without the constraint from reactor. But the reactor experiment also measured delta atmospheric. And I have a question. Do you include also that information in the analysis when you include the constraint from theta to, I mean, when you include the information from theta to 3?
Yeah, we don't.
Okay.
No. This has been discussed, and there have been internal checks of this, but it hasn't been used in any public analyses. There is an ongoing discussion about that. Yeah, so my maybe slightly, you might have to correct me here. My memory is that in the sort of last reactor results, at least from Daya Bay, the correlation between theta 1,3 and delta m square 3,2 was less strong than previously. So we used to be much more worried about it, but because of that lack of correlation now, we got less worried about it. So it is something that's discussed, but I think internally we're less worried because of that. But if maybe you know better whether that's a really important difference. But okay.
Do we have any more urgent questions? Alex has his hand up, and he's an organizer, so he's allowed to ask a question.
So I'll try to be brief. I have lots of things that I would love to discuss with you offline.
Okay.
One way to discuss the quality of cross-section studies is to say not only if you've been able to find a tune that's closer to the data, but to be able to identify tensions or even mistakes in the current models. So in our program, we had early on in week 2, we had a very beautiful talk by Daniel Ratterboris from Minerva, and he showed some of the studies where no tune of any generator on the market is able to reproduce some aspects of the data, even close. I think that's hugely significant. And similarly, when you do electron scattering comparisons, you can really identify flaws in the frameworks. Mm-hmm. So I'm just curious whether you guys are at the level, or if you looked at from that prism where you can identify not just the best tunes, but places where you can invalidate or constrain some of the models. I mean, maybe at some point you can get to this idea that you see the axial form factor that cannot be tuned to the old dipole, or that the Valencia model is wrong. I mean, have nothing against those specific things and models. I'm just saying, is the level of sensitivity when you take your data and you fine grain it, where you look at double differential distributions with details on the hadronic final states, are you going to be there where you can start constraining or invalidating models?
Yes, so certainly, okay, I'll split this into two things. Firstly, as far as our cross-section measurements go, certainly that's true. That's certainly something we're doing. As far as the oscillation analysis goes, which I think was the main thrust of your question, we put a lot of work into trying to identify the problems in the model that we have based on external data sets. So we add a lot of uncertainties that are not necessarily well physically motivated to check if that sort of thing would be a problem. So for example, we take the Valencia 2p2h model and we say, okay, so this is what we have, but we don't have particularly sophisticated uncertainties. So what could be problematic? So in our case, because of the way we reconstruct the neutrino energy, there's a big difference in how, in the bias to that energy estimator based on whether there's an intermediate delta. And so what we did is we recognized that, and we added a lot of additional parameters to just pull that around quite violently, but not necessarily in a well physically motivated way, just to see if that caused a difference. If we don't understand this property, would it give us different results? And what would happen in the fit? So I think that the model that we vary is we kind of affectionately refer to it as a Franken model, right? It's like a Frankenstein's monster in some sense, because we're adding things to not necessarily to put in well-motivated effects, but to check whether an issue like this would be a problem. And so we try and mitigate it in that way. And so I think because there's a difference in that philosophy to taking sort of first principles models and comparing them to our data and saying this is problematic, I think they're kind of distinct. But hopefully that answers your question.
Well, yeah, no, you need both. If you take this thing that you just mentioned, how much of the final fit region is sensitive to these uncertainties? If I were to imagine that my nuclear model is exactly perfect, would the allowed region shrink as a result? Would there be more? What's the contribution to the overall error budget from this exercise?
I think that is quite challenging to give a quick answer to, because all those systematics are correlated. So it's hard to say what the individual contribution is. We do, certainly if a parameter is pulled in the fit, in the near detector fit, or in the far detector fit, but it's normally at the near detector. If it's pulled in a strong way, particularly if it's one of these ad hoc parameters that we put in, we will run additional fake data studies to see what the impact would be. So to go back to this example of messing around with the 2P2H contributions, we did have a strong pull towards delta-like kinematics. And so we massively increased that and ran the analysis to see what would happen. What else would be pulled to compensate and what would happen in the oscillation parameters. And so we try and verify that those choices and certain changes, particularly those that are being pulled, can't have a large impact which go beyond our stated like our uncertainties, like encapsulated in the sensitivity contours. But the focus of that effort is to ensure robustness of the oscillation result rather than diagnosing the problem itself, if that makes sense. We also, I should say, after each round of analysis, we try and figure out what went wrong and then go back to other experiments' data to try and see, is this possibly a weird artifact of what we're doing in the fit? Is this maybe a real physical effect that we can see in other people's data? Is that supported elsewhere? And if not, can we shore up any discrepancies for the next round? So there's kind of an iterative process, but we're focused on, there's an iterative process to improve the model, but when we do the analysis, we're very focused on ensuring that we're not biasing the oscillation result rather than extracting, a good cross-section model that can be propagated elsewhere.
Okay, so we should thank Callum again because we've gone over time, but that's fine.